Jai Hind, welcome to class of Analog and Digital Communication. This is lecture 6 and today we'll be talking about double sideband suppressed carrier, single sideband and vestigial sideband. We know that double sideband suppressed carrier is a variant of conventional AM. It's a variant of AM where sideband is suppressed before the amplitude modulated wave is transmitted. And the prime reason for suppressing the carrier is to save power. As in the previous lectures we have seen that most of the power, that is for a perfect modulation case, we have seen that 2/3 of the total power gets wasted in transmitting the carrier only. So in order to save that power, what we can do after performing modulation, we may suppress the carrier amplitude so that what do we transmit will be consisting of my necessary information, and the power wastage because of the carrier amplitude will be suppressed and could be saved. Double sideband suppressed carrier denoted as DSB SC. We can simply generate it with the help of a product modulator. If I consider my message signal and carrier wave both as cos waves, by simply multiplying both the waves, the resultant that I get will be, we know that applying cos formulas in trigonometry, cos A into cos B, we get cos A plus B plus cos A minus B. So what we'll be getting is, here the two frequency components will be FC and FM, that is carrier frequency and the message frequency. So the upper sideband that we get will be FC plus FM and the lower sideband that we get will be FC minus FM. So product of these two waves can simply give me this is the symbol for product modulator. If I simply multiply my carrier with my message signal, what I'll be getting is the two sidebands, that is my upper sideband and lower sideband. Right? The modulated signal ST undergoes a phase reversal whenever the message signal crosses 0. That will be the case of your overmodulation. Right? The envelope of DSB SC modulated wave is different from the message signal, which is true. It will be like that of the modulated waveform. And when we see the Fourier transform, we want to see the frequency spectrum of it. This will be this equation. With the help of this expression, I can see the frequency spectrum for me. Here, these are the two sidebands. So this being my message signal, this being my modulated waveform. Here, if this is the spectrum showing of message, which is expanding in bandwidth from -W to W, the bandwidth required for AM transmission is 2W, right? And this is the spectrum for my modulated wave, where I am showing the lower sideband and upper sideband here on both the sides. This will be upper sideband here, lower sideband, right? Upper sideband and lower sideband on both sides we are showing. Now, how to generate double sideband suppressed carrier? We can generate it using simple product modulator. But in practicality, no simple product modulator is used because there are so many things associated, like accuracy of the signal that we achieve, the quality of the signal that we achieve. So in order to use it for commercial level, for better applications, we may use two types of generators which we will be discussing here. One of the prime generators used for your double sideband suppressed carrier is a balanced modulator. This is the block diagram for balanced modulator. Here we are using two AM modulators or two product modulators, right? And I may name these as my in-phase channel and quadrature channel, right? Why? Because to one of the product modulator I am providing my message as it is, to another product modulator I am providing minus of my message, right? Here I may use plus minus sign, then I will be using my carrier wave as it is. If I am using it as a simple summer plus sign, then to this channel I will be using phase reverse, 180-degree phase reverse form of my carrier. That is, instead of cos, I might be using sine here if I am using plus here, right? Here I can consider for plus both carrier as it is, for minus this will be subtracted here. So this is taken care of with the help of such kind of geometry, right? So this is the summer circuit. Output of first AM modulator is named as S1T and output of second AM modulator is named as S2T, right? Both are combined here, and what do we get here is my DSB SC. That is my resultant waveform is double sideband suppressed carrier. Balanced modulator consists of two identical AM modulators. These two modulators are arranged in balanced configuration. Why this is called balanced modulator? Because this is arranged in balanced configuration in order to suppress the carrier signal. Hence, it is called as balanced modulator. True, as the name suggests. The same carrier signal CT equals to AC cos 2 pi FCT is applied as one of the inputs to two AM modulators. The modulating signal MT is applied as another input to the upper AM modulator, right? Whereas the modulating signal MT modulator is whereas the modulating signal MT or we can say the minus of MT is applied to the second modulator, to my second modulator, right? Output of the upper AM modulator comes out to be S1. How can I see S1? Let's see. S1 will be simply multiplication of M2 with CT, right? So, this is a waveform, this is an expression for my amplitude modulated waveform. ST equals to AC into 1 plus KAMT cos 2 pi FCT, which we are pretty familiar with, right? If I consider the output of my second modulator, what here I have to consider one thing, that here my message signal is minus MT. So when I multiply these two waves, what I will be getting, S2 will be AC into 1 minus KAMT cos 2 pi FCT, right? So S1 and S2 I get as output of modulator 1 and modulator 2. What happens next? We get the DSB SC wave ST by subtracting S2 from S1, right? And the summer block is used to perform this operation. Right? S1T with positive sign and S2 with negative sign are applied as input to summer block. True. Thus, the summer block produces an output which is the difference of S2 and S1, which is true. Here, what can I write as ST? ST is S2 minus S1, right? So, here or S1 minus S2 I can write. So, this is my S1 and minus of S2. This is my S2. So, if I expand it further, I do get this expression, and when I simplify it, finally I get this, right? So, here what I can see, this is simply multiplication of my message signal and the carrier wave MT into AC cos 2 pi FCT. What I get is some integer value, some constant value which comes as coefficient of this expression. So, that will only be affecting the amplitude level, the magnitude value. Rest I can see that multiplication of two cos waves will give me side waves only, that is upper sideband and lower sidebands, right? We know that the standard equation of DSB SC wave is this. Only here it is getting multiplied with some coefficient that will be affecting only the DC component of it, right? By comparing the output of summer block with the standard equation of DSB SC wave, we'll get the scaling factor as 2Ka. So, this is the scaling factor that gets added to my standard DSB SC and which can be taken care of, right? So, this is how we generate DSB SC using balanced modulator. Another kind of modulator that we may use for generation of DSB SC is my ring modulator. My ring modulator will be a combination of 4 diodes, right? So, this circuit represents my ring modulator. From here, we do apply my modulating wave, which is MT, and it will be mutually induced here with the help of these two primary and secondary coils. Here I can see the direction of diodes. These two diodes are applied in this manner, and in the shape of this ring, two more diodes are applied, right? We can name them as D1, D2, D3, D4. Here how it will act? For positive half cycle, these two diodes may be acting as forward bias, but for the negative half cycle of the input applied, these two diodes might act as forward bias. So in both the cases, we do get some resultant voltage induced at this point, and that can be taken as output from here, right? This is my message waveform. Here the carrier used is a train of pulse, and the output of DSB SC can be represented like this, right? Amplitude of this pulse train will vary with respect to the message signal, which is a sinusoid wave, right? Ring modulator, it is one of the most useful product modulator, right? It is very famous. The diodes are controlled by square wave carrier. Here this carrier is a distinct kind of carrier I am using, not a sinusoid, but we are using square wave in case of ring modulator, right? Diodes are controlled by square wave carrier of frequency Fc. True, frequency is Fc, which is applied longitudinally by means of two center tap transformers. I am using two center tap transformer, transformer number 1, transformer number 2, right? If the transformers are perfectly balanced and diodes are identical, then there is no leakage of the modulation frequency into the modulation output. True, there is no leakage. If we talk about the, we have to consider the situation to be ideal. That is, this is perfectly balanced and diodes are my ideal PN junction diodes. How the circuit operates? Assuming the diodes have a constant forward resistance, RF, which I represent by RF. When switched on, and a constant backward resistance RB, when switched off. We are considering when my diode is in on position, forward bias, the resistance it offers is RF for forward bias, and when it is off, the circuit is open circuit, then it is in reverse bias, then the resistance offered by the diode is represented as RB. This switch as the carrier wave CT goes through 0. So for positive half cycle of the carrier, it acts as forward bias. For negative half cycle, it acts as reverse bias. But we have one advantage here. We are using combination of 4 diodes. So in case of positive half cycle of carrier, 2 diodes will be acting in forward bias. But for negative half cycle, another 2 will be acting as forward bias. So it will be conducting in both the cases. One half cycle of the carrier wave, the output diodes are switched to their forward resistance, true, and the inner diodes are switched to their backward resistance. We are talking, these two are my outer diodes. So for the positive half cycle of my carrier, this is forward bias, this is forward bias, and these two are reverse bias. But for the negative half cycle, this is forward, these two are outer two are reverse bias, right? On the other half cycle of the carrier wave, the diodes operate in the opposite condition, true. So output voltage has the same magnitude as the output voltage, but they have opposite polarity. So it acts as a commutator. We know that commutator is an electrical ring device which operates in the similar manner, right? So square wave can be represented with this expression. We know that the pulse remains on for particular duration and then goes to 0. The ring modulator output then therefore could be, as we know that for DSB SC, output is carrier into message. So multiplication of these two will lead me to this expression. So this is sometimes referred as double balanced modulator, right? Because it is balanced with respect to both the baseband signal and the square wave carrier. So here the circuit is governed by the carrier wave in carrier wave cycle, right? Assuming that MT is limited to the frequency band which is lying from these are the highest frequency content of message minus W to W, the band the spectrum varies. The spectrum of the modulator output consists of sidebands around each of the odd harmonics of square wave carrier MT, right? To prevent sideband overlap, this is a required condition. This is a required condition for any kind of AM, that your carrier frequency must be much higher than my message frequency. Now, what we can do later, we can use after that generation, we might use some band pass filters for extracting out the desired frequencies. We can use a band pass filter of mid band frequency FC and bandwidth 2W. So, if the resonant frequency of my filter that I am using is FC, so it will pass on the frequencies which are centered around FC. It will pass on FC plus FM, it will pass on FC minus FM, as FM is much lesser than FC. So, it is oscillating around FC, right? And what is the bandwidth that it passes? That is 2W to select the desired pair of sidebands around the carrier frequency, right? Such kind of spectrum I can see, like around every integer multiple, like around FC it should be lying from minus W to plus W, that is bandwidth is 2W, which is the standard bandwidth of my AM. So, in case of double sideband suppressed carrier and in case of conventional AM, my bandwidth remains same. Even conventional AM uses 2W bandwidth, even my double sideband suppressed carrier uses 2W bandwidth, right? Now, the next question is how to demodulate such kind of waveform. For demodulation, we may use coherent detection. Now, the question is why this kind of device is called coherent detection. We know the literal meaning of coherence. Here, coherence signifies that the local oscillator at my receiver end used for generation of a wave which is coherent in phase and frequency to the carrier which was used at transmitter. Are you getting the point? Here, coherence means coherence in phase and frequency. Which wave? Carrier wave. Let's see, this is my receiver part. At my receiver, what happens? The first block that I used is a product modulator again. To product modulator, the input will be modulated wave. Here is my transmitter, here is my receiver. I am transmitting wave. I am performing modulation here. My waves are traveling, it reaches the receiver. When it reaches the receiver, what do I receive? I receive modulated wave. So, to my modulated wave, the first entry is a product modulator, and we know to product modulator there are two inputs. So, one of the input is my modulated wave, another input that I purposely provide will be my will be a wave which is coherent in phase and frequency to the carrier which was used at transmitter. Now, in actual practical scenario, my transmitter and my receiver are geographically separated. I am making a call to one of my friend in US. I am the transmitter here, the receiver will be in US. So, these two are geographically separated, but the receiver used at that point will be having an oscillator that will be generating a wave which looks like the carrier wave which was used at transmitter. And in what sense it is similar? In phase and frequency, right? So, I am not representing it with CT, I am representing it with C-T because my motive is to make C-T exactly equal to CT, but there are some practicality, some limitations to it. So, one of the two inputs is ST, another input is my carrier wave, right? And what it generates, my product modulator, if I am giving if this is a product modulator, I am giving two inputs A and B. What kind of output do I expect? I do expect A into B, A minus B, A plus B, AB square, A square B. There are several harmonics that I will be receiving. But next, how do I select the frequency which is desired for me, which is useful for me? That I can decide by selecting a filter of the desired bandwidth and frequency. So as this is a receiver, I use a low pass filter which is tuned at a frequency which is frequency of my message signal, right? So there are three things that we are using: a product modulator, a local oscillator and a low pass filter. Why we are calling it local oscillator? Because we are generating carrier here locally, coherent in phase and frequency with the carrier which was used at transmitter, right? So this is the technique of coherent detection. With the help of low pass filter, I will choose the frequencies that are similar to my message frequencies. So this way I can perform demodulation of my DSB-SC. It is assumed that the local oscillator signal is exactly coherent or synchronized in both frequency and phase with carrier wave CT used in the product modulator to generate ST. This method of demodulation is known as coherent detection or synchronized demodulation. This is also called as synchronized demodulation, because here my demodulator is synchronized, well synchronized with my transmitter. Although they are geographically separated, but this we have tried to maintain the synchronization. So let's see for a little more detail of it. If I see this is my VT. What is my VT? VT is simply multiplication of ST into with C dash T. So I can see one more thing that we must take care of. My CT was AC cos 2 pi FCT, but here C dash T I am representing with AC dash cos 2 pi FCT plus phi. We are assuming that there could be some error introduced in the phase which I am representing by plus phi, although the need is to decrease that phi to 0. So by the end of the expression and derivation, we tend to make that phi 0. If that phi is 0, we are generating a perfectly synchronized, perfectly coherent carrier. If that phi is too high, then there is so much of error introduced, right? So somehow, although we want that this phi should be 0, but we have to represent it. Vt equals to AC cos 2 pi FCT plus phi into ST. What is ST? ST is again MT into cos 2 pi FCT plus phi. I am assuming AC also I am assuming, or for my ease I might assume it to be magnitude to be 1. In few books you might see that they are assuming this to be 1 for their ease of calculation, right? That is possible because magnitude part we can always control and manage easily without using much complex circuitry. So this is the spectrum of my modulated waveform. When I expand this, I do get this. This is simply first, what do I get? This MT I am using with this part and again with this part, right? So I can see that with the help of this coefficient that my magnitude is this much. So I have to represent my magnitude level this, right? And as it is DSB-SC demodulated to message. So DSB-SC spectrum, if I check, the bandwidth expands, the bandwidth is 2W, right? W is the message frequency or message bandwidth, right? On both sides we can see with every integer multiple. So in the first term of equation 3.18, it is removed by low pass filter. First term, you can see, as it is demodulation and it has some carrier frequency, that will be rejected, removed by low pass filter, provided that the cutoff frequency of this filter is greater than W, true, but less than 2 Fc minus W. This is the band gap that we have to maintain. This is satisfied by choosing Fc much greater than W, which is always a necessary condition for AM generation and detection. So V naught T will be 1 by 2 of AC dash cos phi FMT. Now let's see what should be the value of my phi. Initially I discussed that phi should be closer to 0. We know cos 0 is 1. So if I am able to make it close to 0, I am getting exactly the value cos of empty, right? V02 is proportional to empty. From here we can see this is proportional to empty, right? When the phase error phi is a constant attenuated by a factor equal to cos phi. So when do I get maximum value of this? When this is equal to 1, when phi is 0, cos of 0 is 1. Then what do I get? V0 equals to half of AC dash empty, right? This is what I get. But let's suppose phi becomes 90. There is so much of phase error introduced. Cos of 90 is 0. When cos of 90 is 0, this complete term becomes 0. So what do I get in output? V0t. This V0t. What do I get? Nothing. So if some error is introduced here in choosing the local oscillator frequency, in generating this waveform, so that phi has a bigger value, that if phi is approximately plus minus pi by 2, then what do I get as output after demodulation? Nothing. I get nothing. So that will be the case of maximum error. So when the phase error is constant, the detector provides undistorted version of the original baseband signal, right? In practice, we usually find that phase error phi varies randomly with time, and due to random variations in communication channel, the result is that the detector output, the multiplying factor, also varies randomly with time, right? So this can be done with the help of perfect synchronization. So that's it for today. We continue later. So these are the references that I have used. Thank you.